My name is Nick Hudyma, and I'm a faculty member at Boise State University. Next on Summer School, I'll be talking about rock slope instability. Welcome to Summer School 2025. My name is Nick Hudyma, and I work at Boise State University. Today, we will be discussing kinematic analysis for planar instability in rock masses. It's summer. It's hot. Beaches are crowded, and you need to get away. Where do you go? You go to the mountains. Grab your loved ones or your furry four-legged friends, and let's head out. Finally, you make it to the mountains and you see beautiful outcrops and rock masses. Isn't Mother Nature wonderful? Then, your engineering brain kicks in and you start thinking, is this rock slope even stable? Let's examine a simple two-dimensional road cut and visually assess stability. On the left-hand side, you'll note the rock may slide into the roadway. It is potentially unstable. However, on the right-hand side, the rock cannot slide into the roadway. It's stable. You may be thinking that this is simply a block on an inclined plane problem from your first physics course. Well, I'd tell you you're on the right track, but let's get a little bit more in depth. Today, we're going to cover 6 topics related to kinematic analysis. First, we'll provide a quick overview of kinematic analysis. We'll talk about rock masses and we'll talk about discontinuities. We'll talk about properties of joints that we need for our kinematic analysis. Finally, we'll talk about stereo nets and how we can plot geological data. And finally, we'll assess planar instability using stereo nets. First, kinematic analysis. A kinematic analysis incorporates the orientation of discontinuities and their friction angle to assess stability with respect to the orientation of a rock slope. We use a stereo net, which is a graphical technique that allows us to investigate planar, wedge, and toppling failure modes within the rock mass. The analysis does not provide a factor of safety. Rather, it indicates whether failure is likely to occur. For this summer school session, we're going to focus on planar failure within rock masses. A rock mass is a system of blocks that are separated by discontinuities. These form a discontinuous material that behaves as a unit. The discontinuities control the engineering properties and behavior of the rock mass. The presence of discontinuities is the key characteristic that distinguishes rock masses from soil deposits. If you look at the picture on the right-hand side of the slide, you should notice how the rock mass is divided into discrete blocks. Next, we have to talk about discontinuities. I like to classify discontinuities into 2 broad categories. Structural discontinuities are defined by a pair of surfaces, sometimes referred to as fracture walls, that have been displaced either by opening or by shearing from their original positions. For example, fault displacement, which we can see down in the lower right-hand corner of this slide, occurs predominantly by shearing. Bedding planes that were once intact may become separated due to stress relief. And we can see on the upper portion of the slide right here, the classic example of bedding planes. Now, on the other hand, we have integral discontinuities, which are planar features within the rock mass that, while not necessarily open or weak, can significantly impact the overall stability and behavior. These discontinuities may evolve into structural discontinuities. For example, we may have foliation or schistosity in a metamorphic rock mass, or in sedimentary rock masses, we may have intact bedding planes. For this summer school session, we're going to focus on joints. Joints are structural discontinuities that have opening rather than shear displacements. They're formed by stresses acting on the rock mass. Joints are planar features that occur in sets. Joints within a joint set will have similar spacings and orientations. But this is very important. The orientations and the spacings are similar, not identical. There may also be multiple joint sets within a rock mass. In addition to joint sets, there's often non-systematic joints which are present within a rock mass. If you look at the picture on the right-hand side, you should see well-developed vertical and horizontal jointing within columnar jointed basalt. To perform our engineering analyses and understand the behavior of a rock mass, we need to know the properties of the joints. I like to group joint properties into three broad categories: geometry, joint wall surface condition, and mechanical properties. As you can see by this slide, there's a number of joint properties spread throughout these three categories that we really need to understand for rock mechanics and rock engineering. However, for our kinematic analysis, we need to know the orientation of the joints and their friction angle. For our kinematic analysis, we obtain the orientation of joints through field mapping. This may be through physical measurements. We go out to the rock mass and we take the orientation measurements we need, or we may get them by assessing point clouds from LiDAR or photogrammetry. The key part of this is that we're going to make many orientation measurements, not just one or two. Okay? We also need to obtain the friction angle. We obtain the friction angle through testing, and we're going to test several joints within each joint set to determine an average friction angle. First, let's talk about orientation. I think this is the most challenging aspect of kinematic analysis. Okay? Recall that joints are planar features, and they're going to have an orientation in three-dimensional space. We have two common methods to describe the orientation of joints. We can use strike and dip. This is a convention often used by geoscientists. Or we can use dip and dip direction. And this is a convention that's often used by geotechnical engineers. Since we work quite often with geoscientists, we should be familiar with both measurement techniques. Let's start with the dip. The dip is a measurement of inclination in a vertical plane. It is measured downward from a horizontal plane. The dip, or commonly known as the dip angle, ranges between 0 degrees and 90 degrees. The strike, or the dip direction, is an azimuth measurement on a horizontal plane. It is measured from north, right, either 0 or 360 degrees in a clockwise manner. Let's take a look how these measurements are made. Let's begin with a block diagram with a north arrow. The top of the block, which is shaded gray, is a horizontal surface. We need the north arrow for our azimuth reading, which is our strike or our dip direction. Next, let's add a planar feature. The planar feature intersects the horizontal plane and is inclined at an angle downwards from the horizontal plane or the horizontal surface. Having this diagram, we can now determine the dip of the plane. In the figure, we see a black line, which is located on the horizontal surface or the horizontal plane, and a green arrow, which is on the dipping plane. The angle between the line and the arrow is known as the dip. The dip value ranges between 0 degrees, the plane is horizontal, and 90 degrees, the plane is vertical. The true dip is the maximum angle the dipping plane makes with the horizontal. Other dip measurements are referred to as apparent dips, which are always less than the true dip. Next, we can determine the strike. Let's draw a parallel line to the north arrow and place that on our block diagram. The horizontal angle between the north arrow and the intersection of the dipping plane with the horizontal surface is known as the strike. The strike varies between 0 and 360 degrees. Now, here's where a little bit of confusion comes in. Since the strike is a line, it can point in either direction. This can cause considerable confusion. To remedy this, we use something called the right-hand rule, which states when looking along the strike, the plane must dip to the right. To remove the confusion of strike and right-hand dip rule, we often use what's known as the dip direction. The dip direction is the horizontal angle between the north arrow and the direction in which the dipping plane is tilted downwards. It can be thought of as the angle between the north angle and the projection of the dip onto the horizontal plane. We can really think about this in quite an easy manner or fashion. The dip direction is the direction a drop of water would roll if placed on the dipping plane. Finally, we have the full orientation of the dipping plane in either strike and dip or dip and dip direction. The strike tells you the azimuth of a line along a horizontal surface, and the dip tells you how steeply the planar surface is tilted. The dip direction, which is always 90 degrees clockwise to the strike following the right-hand rule, tells you the azimuth of the direction the dipping plane is tilted downwards. But hold on, we're not done yet. There's one more orientation measurement that we need to understand. This measurement, or the orientation that we need to understand, is known as the normal or the pole to the plane. Okay? The normal is a line that is perpendicular to the plane. Okay? So a quick recap. Planes, which is a three-dimensional feature, they have a strike and a dip and dip direction. But there's also a linear feature, a line, and that's the normal to the plane, or the pole to the plane. For our kinematic analysis, we also need to know the friction angle of the joints. And there's two ways that we can determine this. We can either use a direct shear test or a tilt test, which is shown on the left-hand portion of the slide. The friction angle is often referred to as the basic friction angle. It does not include the effect of topography or roughness along the surface of the joint. Experiments have shown that the basic friction angle ranges between approximately 25 to 35 degrees. The friction angle is lower for sedimentary rocks and higher for igneous and metamorphic rocks. So, now we have our joint properties: strike and dip, or dip and dip direction, and friction angle. The big question is, what do we do with them? And the simple answer is, we plot them. Okay? And so we're going to take the orientation of our planar discontinuities, strike and dip, or dip and dip direction, and we're going to plot that data on what's known as a stereo-net. Okay? A stereo-net is a graphical tool used to plot three-dimensional data on a two-dimensional surface. Okay? Now this is really important. As we move from 3 dimensions to 2 dimensions, we lose a dimension in our plotting, so our geologic features will also lose a dimension. So what does that really mean for us? Well, what it means is the planes, right, our joints, the orientation of joints, which are planes, they plot as lines. Lines will plot as points. Okay? Now, the nice thing about a stereo-net is the angular relationships between lines and planes are preserved. So we can make those angular measurements on our stereo-net. So how does a stereo-net work? Imagine a transparent sphere with a horizontal plane at its center. So this is what we're talking about, this sphere and this horizontal plane. If we plot a dipping plane, or project our dipping plane from the horizontal into the lower hemisphere, the plane will intersect the outer edges of the sphere. We refer to this as the spherical projection of the dipping plane. So what we see right here, this rectangle, is our dipping plane. This dipping plane intersects the edges of the sphere right here. What we need to do is project the spherical projection onto the horizontal plane. Okay? We want to project it back up to this horizontal plane. To do that, what we do is we project all points along the spherical projection. So all the points along here, we project those back up to the zenith. Okay? The trace the projection lines make with the horizontal plane is known as the stereographic projection of the dipping plane. What happens is our three-dimensional object, this dipping plane, now plots as a line in the horizontal plane. The horizontal plane that we've been talking about in this transparent sphere, that's our stereo-net. Okay? Now, there's a couple components to our stereo-net. Okay? And a stereo-net is shown in this middle portion of the slide. Okay? We have a primitive circle. And that primitive circle is the outer edge of the stereo-net. Okay? Azimuth values are plotted along the edge of the primitive circle. We also have great circles. Okay? And our great circles are analogous to lines of longitude. And so you can see a number of great circles here. And the interesting thing about the great circles is they represent our dipping planes. So if we have a plane, which is a line on a stereo-net, and it plots on the primitive circle, it has a dip of 0. But as we get steeper and steeper and steeper dip values, the lines start to follow a more straight orientation. So you can see if we have a dipping plane of 90 degrees, so a vertical plane, it'll plot right here, and we'll have a straight line. But as the dip angle decreases and progresses to horizontal, we get more and more and more curvature to those lines. Let's take a look at a plot of a single plane. So we want to plot a plane that has a dip of 30 degrees and a dip direction of 90 degrees. Okay. What that means is that this plane is dipping to the east, which is 90 degrees azimuth. The plane has a dip of 30 degrees, and so that plane is plotted along the great circle of 30 degrees. Other thing that we can do is we can plot the pole to the plane. So recall, the pole to the plane is the normal to the plane. The normal to the plane is a line, but because we're plotting it on a stereo net, we lose a dimension, so the pole to the plane becomes a point. Okay? Now, we know the pole to the plane is the normal to the plane, which means it's perpendicular to the plane, which means it's 90 degrees to the plane. So it plots 90 degrees from the line or from the plane. Okay? So to recap, the plane plots as a line, the line plots as a point. Rather than plotting a large number of lines on our stereo net, it's very convenient for us to plot poles to the plane, which are points, rather than the planes themselves, which will be lines. If we plot all of our lines, the stereo net's going to get very messy. Now, recall that joints occur in sets. And when we're in the field, either flying our drone or making physical measurements, hopefully we're doing both, okay, we're going to make numerous measurements, okay? And what we want to do is to be able to plot all of that data on our stereo nets. Okay? It's important to remember that joints within a joint set are neither completely planar nor completely parallel. There's going to be variations in the dip and the dip direction of these measurements. When we plot all of our field data, we can visualize joint sets within the rock mass. The stereo net on the right is a pole plot of the dip and dip direction of joint measurements. And if we look closely, it's clear there are 4 joint sets designated JS1 through JS4. And so if we look at this plot, right, here's joint set 1, and there's the poles to the planes that we measured in the field, joint set 2, joint set 3, and joint set 4. From the pole plots, we can obtain the mean or the average orientation of the measurements within each joint set. Once we have the mean measurement, we can plot the average orientation of the plane on the stereo net. And so what we're seeing on the right-hand side of this plot is the mean plane right here for joint set 1. For the 4 joint sets, the dip and dip direction is shown on the left-hand portion of the slide. We have to be very careful with this, okay? Remember, the plot on the right-hand side is a pole plot. We're plotting the pole to the planes. So, for example, if we examine JS2, right here, okay, it seems that the mean plane would have a high dip because all of the points are plotted near the center of the stereo net. Okay? Remember, though, this, right, all of these points are poles or normals to the plane. And so the mean plane is going to be 90 degrees to the poles. And so joint set 2, we can see over here, has a very shallow dip of 14 degrees, okay, because it's 90 degrees from here. Okay. Now, we know how to plot our data, our joint data, our discontinuity data on a stereo net. We want to be able to assess planar sliding instability. Okay. And we're going to do that using these 3 joint sets that are shown on this slide. To assess planar sliding instability, we need to plot on our stereo net the slope that we want to construct, which we'll plot as a line. We're going to plot the poles to the discontinuities that were mapped, and those poles plot as points. And somehow we need to incorporate friction. Okay? We'll cover that, don't worry. However, before we start plotting, let's review the 4 criteria required for planar sliding instability. For planar sliding instability to occur, 4 criteria must be met. If one or more of the criteria are not met, sliding cannot occur. The 3 figures shown at the top of the slide are meant to help us with the discussion of the 4 criteria. So, criterion 1, the dip of the joint must be less than the dip of the slope. If the joint dips steeper than the slope, it will be stable for planar sliding. Criterion 2, the joint must daylight or intersect the slope plane or the slope face. So, let's take a look at the drawings at the top of the slide. We can see from the middle figure that the joint, indicated by this brown line or brown plane, right, because the discontinuity is a plane, that it has a dip less than the dip of the slope, okay? And it also intersects or daylights on the slope face, okay? Potentially unstable, okay? Criterion 3, the dip of the joint must exceed the angle of friction or the friction angle. Okay. We'll work on that when we get to the stereo net. And finally, criterion 4, the dip direction of the joint should lie within approximately plus or minus 20 degrees of the dip direction of the slope. And so again, if we look at this middle figure, we can see that the dip direction of the joint and the dip direction of the slope are nearly parallel. So visually, not taking friction into consideration, we may have a planar failure, okay? But what we want to do is we want to do this on our stereo net. So let's go to our stereo net and perform our assessment. The slope that we want to construct has a dip of 65 degrees and a dip direction of 150 degrees. We're going to plot the orientation of the slope, and that slope will plot as a line on our stereo net. And the slope is plotted as this orange line. Okay? So far so good. Next, we want to plot what's known as the daylight envelope. This oval shape right here on the stereo net is our daylight envelope. Any poles to planes of discontinuities that plot within the daylight envelope could possibly slide. That's criterion 2. The other thing that you should notice on our stereo net are 2 crossing lines. These 2 crossing lines are plus or minus 20 degrees from the 150 degree dip direction of the slope. These mark the lateral extent of the critical zone. Okay? This is criterion 4. So our slope has a dip direction of 150 degrees right here. So we have 130 degrees and 170 degrees. And we plot these 2 straight lines. They cross through the center of the circle, and they cross through the daylight envelope. Now, these crossing lines cut through the daylight envelope, and they form this red cone. Okay? Any poles to planes of discontinuities in this zone are potentially unstable. Next, we have to deal with friction. In order to incorporate friction onto our stereo net, we plot what's known as a friction cone. It's a circle that's plotted at the center of the stereo net with a radius equal to the friction angle. If any poles to planes of discontinuities plot within the friction cone, they're stable. And that's criterion 3. What you should notice is by adding the friction cone, right here, this red, which was once a cone, is now a truncated cone, right? That red area has decreased in size. Okay, and right, it's colored red or pink because it's kind of the danger zone. Okay, so finally, let's plot the poles to the discontinuities. And so if you recall from a couple slides previous, right, we had 4 joint sets, joint set 1, joint set 2, joint set 3, and joint set 4, right? 1, 2, 3, 4. And what we can see is that any poles to planes that plot within this red zone are potentially unstable. And so from this kinematic analysis, we can see that joint set 1 has some discontinuities that are potentially unstable. Joint set 2, joint set 3, and joint set 4 are stable. But let's do an assessment on this. And so what we have is a table that contains the 4 criteria for planar sliding, the average dip and dip direction for the 4 joint sets, as well as the slope orientation and the friction angle. Recall that for sliding to occur, all 4 criteria must be met. Okay? In the table, a possible answer is highlighted in red, indicating the criterion is met and sliding is possible. A not possible answer in the table is highlighted in green, indicating a criterion is not met and sliding is not possible. Okay, and so what we can see is that we have our 4 criteria up here, The first one, is the dip of the joint less than the dip of the slope? Second one, does the joint daylight? Okay. Basically, here we're asking, do the poles to the planes plot within the daylight envelope? Next, is the dip of the joint greater than the friction angle? Okay. Basically, we're asking, do the poles to the planes plot within the friction cone? And then also, the last one is the dip direction of the joint plus or minus 20 degrees from the dip direction of the slope, right? Those are our two straight lines that we see here. Okay. And so we see, yes, our slope is potentially unstable, right? Sliding failure may occur along joints in joint set 1. And so the big question is there anything that we can do? And from a kinematic assessment perspective, there are some variables that we can change and others that we really cannot change. For instance, we really can't change the friction angle. Okay, that we ran some tilt tests, or we ran direct shear tests, and we measured that friction angle. Okay. The other thing we cannot change, or probably can't change, is the dip direction of the slope. Right? We want our slope facing a certain direction to correct for topography or something like that. Okay. However, and if we look at the stereo net on the left-hand side, one of the things that we can change is the dip of the slope. And this stereo net on this slide is plotting a slope with the same dip direction, but a dip of 50 degrees, not 65 degrees. And if we change the dip to 50 degrees, we see the poles to the discontinuities on joint set 1, they no longer cause planar failure. And we may say, that's awesome, right? We've solved our problem. However, now we're really laying back that slope so it's less steep, okay, which is probably going to increase our construction costs. And so if that's the case, now we may have to consider stabilizing the slope some way. However, for summer school, we have successfully completed our kinematic analysis for sliding failure in rock masses. We're not done yet, though. We have to have our recap. So remember, kinematic analysis is really the first step in rock slope stability. It incorporates a geometric comparison of orientations of the slope and discontinuities, as well as frictional properties of discontinuities. Here's the big thing. Kinematic analysis tells us if failure is possible. It does not give us a factor of safety. We need some other technique to give us our factor of safety. We can do some kind of limit equilibrium or some numerical analysis for that. Rock masses have discontinuities that control their engineering properties, and this makes rock analysis in rock masses different from that in soil deposits. For planar failure to occur, all 4 criteria must be met. Okay, that's very important. And to perform our kinematic analysis, we're going to plot the slope, which plots as a line. We're going to plot poles to discontinuities, which plot as points. We're going to plot a daylight envelope, a friction cone, and the lateral extent of the critical zone on a stereo net. Any poles to discontinuities plotting outside the friction cone, but inside the daylight envelope, within the lateral extent of the critical zone, are potentially unstable. So before we get out of here, thanks for listening, and I have some acknowledgments. All StereoNet plots for the examples were produced using DIPS by Rock Science. So thanks, Rock Science. Thank you to the Geo-Institute for this opportunity. Hey, consider joining a technical committee. My favorites are the Rock Mechanics Committee and the Engineering, Geology, and Site Characterization Committees. But you probably figured that out by now. Thanks to the many students who have worked with me and inspired me. And a big shout out to former professors Bill Brisbane and E.Z. Laitai from the University of Manitoba, who inspired me to study rock mechanics. We have some references here from where I took some figures, and when I teach rock mechanics at Boise State University, here's a couple books that I always draw examples from. So, what about your homework? Well, there's not really any homework, but what I really want you to do is get out and explore some cool rock masses. All right, thanks for listening, and hope to see you at the next Geo-Congress. Thanks.